time for us to start the session as it's 6 p.m. IST. Let's wait for another minute. I can see that some other people are also joining. Mariam, do you have a question?
Yes.
Yes, please go ahead.
Are we allowed to ask questions from Mr. Salazar?
Of course, you are.
Okay. Thank you.
Yeah, you're most welcome. So let's begin with the session today. Since it's 3 p.m. now, I think most of the folks have joined. Okay, so let me begin. The stars don't look bigger, but they do look brighter. Aerospace is an evergreen industry, and many students inspire to be an astronaut or a space scientist, engineer, rocket designer, and manufacturer, and so much more. But aerospace is a vast field with many career options. It is very essential to explore other horizons in the space industries, and many of the students have unexplored the potential of aerospace engineering. Good evening, ladies and gentlemen. My name is Vani, and I'll be the host of the session today. I work at Hexstar as the head of Department of Aerospace Engineering, and today we have gathered for one of the most requested webinar on the topic Careers in Aerospace Engineering. Today's session will be preceded by Mr. George Solaris, who has experience of 40 plus years in telemetry, communication, speech control, command and data handling, and much more in NASA. And he was the human computer interface technical discipline lead in NASA as well. His passion is sharing knowledge with students and has reached out to up to 16,000 plus students for mentoring and tutoring. The introduction would be too long if I mention all your achievements, sir. The more I praise for you, the less it is. It is my honor to host today's session with a speaker like you. So now I would like you to take over to the session, sir. Thank you so much for joining this evening today.
All right, thank you for the introduction. And I turn on my cameras to let you know that I'm a real person. Again, thanks for inviting me. And I'm going to turn off my camera now so I can get more bandwidth here. When I started thinking about careers in aerospace, I started thinking about my experience with aerospace engineers. Myself, I'm an electrical engineer as an undergrad and systems engineer by and got a grad degree in that area. But I think Vinny mentioned, and correctly so, is that there's different options and ways of exploring a career in aerospace, and and I'm going to share that with you. So what I'm going to be talking about here real briefly is, first of all, what is aerospace engineering? Probably y'all know that, but I'll just start that as a basis so everybody's on the same page in terms of what aerospace engineering is. And then I'm going to switch gears just slightly and start talking about NASA's involvement in aerospace engineering. And so I'm going to, I realize that sometimes NASA is not fully understood in terms of what it is. You know, they call NASA a company. It's not a company. It's a government agency. So, and I was a government employee. So I'm going to give you an overview of NASA involvement in both aeronautics and space. And of course, aerospace engineering can do space as well. So I'll be talking about careers at NASA, and this, could be another company. It could be ISRO, or it could be European Space Agency. But I'm going to give you a flavor of where aerospace engineers have done their career at NASA, and I've had the opportunity to work with many aerospace engineers over the years, and so I'll share that with you as well, and then some final closing remarks. So a disclaimer, just in case there's things about about counseling, career counseling. I am not a certified counselor. I'm going to share just information that I have. If you want to get a specific, more official, let's say, guidance, if you will, I advise you to see a certified counselor. So that's my disclaimer for anything related to careers. So what is aerospace engineering? Well, it's primarily the field of engineering concerned with the development of an aircraft as well as spacecrafts. And so, you have a jet fighter that does atmospheric flight through the atmosphere, but you also have spaceships that also go through the atmosphere. And you have to look at what the application is. The space shuttle launched through the atmosphere, and it's quite dangerous launching through the atmosphere. And then it goes into space where there's virtually no atmosphere at all. But part of aerospace engineering is understanding the environment, and the environment could be the atmospheric conditions all the way up to the ionosphere or outer space. So an aerospace engineer would have a good understanding of the environment. That's really how you can really design a system. You got to know the environment. Something that maybe I'll say over and over again is that there are four key elements in a system design. You got the hardware, you got the software, you got the environment that the hardware and software see, and the human involved there. So you got four elements: hardware, software, the environment, and the human. And that's kind of like a fundamental understanding that engineers at NASA especially have to have when we're designing systems for human spaceflight. So what are the success factors? There are many success factors associated with being an aerospace engineer, and I'm just mentioning a few here. Certainly, you got to have a solid understanding of the design and development process, and every company has different design development processes. They kind of deviate a little bit, but it's important to understand that. And one of the things, whether you're an aeronautical engineer or a chemical engineer or civil engineer or electrical engineer, there's always a process that's very similar to the scientific method. And it's you make observations and you look at what the problem is, and then you form a solution and you come up with options, and then from those options you develop and prototype them and see which one is going to do the job. And if not, then you have to go back and iterate. So it's a very iterative process, and that's what design engineering is all about. It's iterative process of developing a system that eventually gets you to your requirement or your need, if you will. You got to have a strong foundation in math and science, and I have to say that, at least from my experience at NASA, I took a lot of math in school, a lot of math. And but I have to say that for the most part, I never went beyond calculus one. And the science I do have to say that I used a lot of the science, especially developing spacecraft systems. Solid understanding of aerodynamics and thermodynamics, it's a must, especially if you're designing a vehicle that's, let's say, for example, the space shuttle, when it was through the Earth's atmosphere, the temperatures got as hot as 4,000 degrees Fahrenheit. Well, you got to be able to design a system that can withstand those kind of temperatures. And of course, aerodynamics. If you ever saw the space shuttle launch, it would, once it launched, it would turn about 90 degrees and then go up. We call it uphill, launching at a certain angle. That angle of attack is important. So understanding all that is critical. Computer mathematical modeling. I know aerospace engineers at NASA that did quite a bit of mathematical modeling, especially in the early development of some of the spaceships that we were involved in designing. Understanding risk analysis and failure modes of a system. Risk is something that you always have to deal with in a project. And as part of the aeronautical engineering program, at least the ones that I know here in the United States, and it's probably the same everywhere else, is that you get exposed to risk analysis. Okay, what is the likelihood of something failing? And then if there's a likelihood of a failing, what are the failure modes of that system? And knowing those, you can manage a risk. You can manage the possibility of something going wrong by either mitigating it coming up with a solution if it fails in some fashion, or you basically what we call safe mode. Okay, so this is very common in satellites. When they've lost communications with Earth, they go into a safe mode, so that way they don't expend a lot of their battery resources. So understanding those aspects of design and development and the risk associated with that, as well as the possible failure modes of your design, becomes very important. Good understanding of project management skills. I can tell you that quite a few aeronautical engineers, or at least the ones that I know at NASA, that were aeronautical engineers, became project managers and also systems engineers. Just simply because they started to learn the whole aspect of system development, system interaction. That's that bottom bullet. So system interaction sometimes is called systems thinking. Basically, it's the holistic understanding of how one element in a system can affect other elements in a system. And one of the challenges sometimes for especially entry-level students is to understand that they're designing a piece that could affect other systems, and that's the part of system understanding of interaction. So it's very good. It's very important to begin understanding that, and you get it a little bit with experience, but certainly you can study it in school. I think some engineering programs provide a class or two on system development or project management. Sometimes they call it engineering management, but it's an opportunity to learn about the top level overview of a system. All right, so I'm going to kind of change gears just a little bit, and then start talking about NASA and its role in aeronautic engineering space. First of all, you hear the word NASA. They say NASA, NASA. Okay, but NASA is just an acronym. That's National Aeronautics. That's the first A, which basically deals with research aircrafts, and we, they do quite a bit at a certain center called Langley Research Center, as well as another one called Armstrong Center, and I'll show a map of where all the NASA centers are. And then Space Administration. Okay, so the space part, and that's the part that I was involved with for many years. And that was, like for example, the Saturn rocket for the Apollo space program, the Space Shuttle program, which is what I got my start in. International Space Station, which I was involved with the design of audio systems, and then the commercial part, SpaceX. I was involved with SpaceX, and also with the Orion spacecraft, and also the Starliner from Boeing. So and then the Human Lander system. That was my last project before I retired, and that was basically that's going to be the taxi that's going to take the humans from the orbiting moon station down to the Earth, run down to the surface of the moon, and then once they're done, they're going to go back up into the orbiting moon station, and then get into the Orion spacecraft, and then return to Earth. As you can see, the Starship is a big ship. You know, there's the people down there at the bottom of the spaceship. It's a big rocket. It's about 150 feet long, roughly. So anyway, that's the space part as well as the aeronautics part. But I can tell you that aeronautical engineers from working aircraft have also worked in the space area, and people in the space area have worked in the aeronautics area. So they kind of interchange each other. So here is NASA. When you say NASA, this is the picture I see in my head. This is NASA, and it's made up of centers all over the United States. I'm in Houston, Johnson Space Center, down there at the bottom, Texas, but there's other ones as well. I'm not going to say all of them, but like, for example, Kennedy Space Center is out in Florida, and that's where we launch, SpaceX. We've launched the shuttle there. In fact, we launched the Apollo space program from there, and it's a good spot to launch spaceships into a specific orbit around the Earth. And then on the far left side, one of the big ones there is Jet Propulsion Laboratory, and their area is primarily in the area of robotics. Like, for example, the Mars 2020 Perseverance, all those rovers that are on Mars right now were designed and developed by Jet Propulsion Laboratory. Right below there is Armstrong Flight Research Center, which they deal with high velocity, high speed aircraft. They work very closely with Langley Research Center in developing high performance aircraft. One of them is, I think it's the X-59 that, is flying like 4 times the speed of sound, and it's just incredible having to deal with those kind of speeds, and what it does to the aircraft in terms of the structure. So having good aeronautical engineering experience under your belt is obviously very important. All right, so engineering from a spacecraft standpoint, at NASA, I've been involved with these different areas. Certainly electronics are the brains, if you will, of a spaceship. And you have to have a good understanding of what electronics, how to operate, how to design electronics, how to deal with the thermal effects of electronics. I had to learn a little bit more of thermodynamics than I thought I was going to need it, but it's good to know all the aspects of designing electronic systems for space vehicles, and the same goes for atmospheric jet airplanes as well. The thermal effects, how do you protect against overheating? The space shuttle had a very sophisticated thermal tile system that protected it as it was re-entering the Earth's atmosphere at 20,000 miles per hour. Propulsion has a combination of the aeronautical engineer, the structure engineer, the electronics engineer. From a structure standpoint, you got to build very strong metal systems that can withstand the pressure and the vibration of an engine igniting. You have the aeronautics aspect of thermodynamics, of transferring a lot of the heat that heats up when those engines fire. And then you got the electronics that are controlling the throttle of that engine. And so, it's watching how much oxygen is being pumped, how much hydrogen, the temperatures, all kinds of things going on there. And aeronautical engineers have to have an awareness of all that. And that's part of the design process, is really becoming more multidisciplined than having a specific design. I can tell you that at NASA, a lot of our engineers, they graduated with a chemical engineering degree, or me, like electrical engineering degree, but we came to learn about the other disciplines. And that's really the only way that you can design sound, reliable systems, is by having many eyes from different disciplines looking at the design from a different perspective. Guidance, navigation, and control down there at the bottom. Aeronautical engineers, and I've known, oh gosh, maybe 5 or 6, that did a lot of guidance, navigation, control, developing mathematical models of how a spaceship is going to fly into space and land on the moon and all that. And so they use quite a bit of mathematics, quite a bit of trigonometry, geometry, a little bit of calculus 1. But they also have to understand what they're modeling, and if it's realistic. You can model something that goes at 100 times the speed of sound, but if the structure, there's no structure that can handle that. So you have to have a good, let's say, practical aspect of engineering, not just the theoretical. I can tell you that in school, I was taught a lot of theoretical stuff, but when I started to work in NASA, I started to see, at least for the work I was doing, that it was not as hard as the classroom material was. It turned out to be a little bit easier. And then having practical aspects of it is also important. Like for example, a electronic circuit. They were showing a picture of a beautiful square wave, and this was the electrical output of a computer board. But in reality, that square wave is more. It looks noisy as heck because of the effects of interaction with other systems and other wires. Wires behave very weird at high speed, and so it becomes a matter of practicality of what you understand about wiring, what you understand about separation of wires in electronic systems, and all these. You can call them rules of thumb that you learn on the job that are not taught in school. Robotic systems. I love robotics because it's got different disciplines involved. It's got the structure. Obviously, you got to have a structure of a robot. Then you've got the the guidance and navigation control aspect of guiding this robot using sensors, to guide it walking around. And of course, you got the electronics as well that are used to activate the actuators and all that kind of stuff. So robotic systems are pretty cool in terms of multidiscipline. And I would say that somewhere in the vicinity of half of the engineers I know that work robots are aeronautical graduates of engineering in one fashion or another. All right. Other specialized fields of engineering at NASA, fabrication. So, sometimes we, I guess in school, don't give you much, let's say, training in fabrication, but, fabrication is critical. And, you can have the best design on paper in the world, but if you cannot fabricate it correctly, you're going to cause a potential accident. And there's just too many cases to share with you, but there was one in it was called the Genesis, and the Genesis basically retrieved an asteroid sample and then came back to Earth and landed in the United States in Utah. Well, it crashed, and the reason it crashed was during fabrication, a sensor to detect the gravitational force field, or the gravity of the Earth, was put upside down. And because it was put upside down, it did not deploy the parachute in time before it crashed. It was just a bad fabrication. there's other incidents that have happened in terms of bad fabrication. So fabrication becomes important. And I knew two aeronautical engineers that got into the manufacturing of spacecraft systems. So they would work with engineers in making sure they understood the design, making sure sensitivity of fabrication processes, and put that down on paper to make sure that nobody overlooked a parameter that was critical for manufacturing that part. Materials, aeronautical engineers, get involved with the materials aspect. You can have strong materials, but if they're too heavy, it may not work in a space flight. One of the things about space flight is that it's very expensive to launch based on how much it weighs. Roughly at this point in time, I think the last figure I saw was $10,000 per pound. So it gets very expensive to launch a vehicle or a system as it starts getting heavier. So we have to design for lighter materials, and that's part of the aeronautical engineers getting involved with the materials folks in developing those kind of systems. Tests, oh my gosh, tests. That's another biggie. Just like fabrication, if you don't test, there's a chance you're going to miss a error in the design, the fabrication, or whatever. Give me an example. Mars Polar Lander back in 1990, I think, crashed on Mars. What happened? Well, there were these sensors on the landing legs of the Mars Polar Lander that were supposed to detect when they touched down on the surface of the Mars surface, and they shut off the engines. What happened was they decided not to test those sensors on the legs when the legs deployed. When the Mars Polar Lander dropped its legs, getting ready to land, it caused the sensors to shake a little bit. We call it kind of like a vibration, and it caused spikes in the signal that the computer said, "Oh my gosh, I landed. I need to turn off the engine." Well, it turned off the engine when the Mars Polar Lander was something like 200 feet, still above the surface of Mars. What happened? It came crashing down because the engines had been turned off. Okay, so EVA suits. An EVA suit is kind of like a spacecraft for one person. You got life support systems, you got communication systems, you got structure systems. Let's see, what else? You have, obviously, you have to deal with information that's feeding the astronauts in terms of the health of the suit. And so EVA suits is another area where aeronautical engineers get involved with the different portions of the suit. And I know that in our Crew and Thermal Systems division there at the Johnson Space Center, there were about 3 aeronautical engineers that I worked with for many, many years. And they were very good, not only in aeronautics, but they were really good also in electronics design. I was amazed, how well they knew electronics. But they came to learn that because that was part of their job, is to understand all the pieces that come together. And then again, it goes back to being multidisciplined. All right. Now, down there at the lower right hand, you see systems engineering. This is a big, big thing at NASA. Understanding the systems engineering process is part of systems thinking, but it's a methodical way of developing a system. Very similar to the the scientific method, right? Scientific method is you make observations, form a hypothesis, design an experiment, perform the experiment, gather the data, compare the data against the hypothesis, and either you change the hypothesis or you change the experiments and try to arrive at a solution of what went wrong. Same thing with systems engineering. On the left-hand side is what we call the system design process. And so we get something called requirements. Okay, requirements is what the system should be doing. And then from those requirements, we develop possible solutions for it. And then those possible solutions, we do trade studies, analytical analysis to see which is going to be the best design. We prototype it, we test it, and we compare it against the requirements. Is it accomplishing what the system is supposed to be doing? If everything goes okay, then we go to the right-hand side of the V, product realization process. That's where you actually start fabricating the actual system. And it gets really expensive on the right-hand side. It's, the cost can get dramatically expensive compared to the left-hand side, which is the design process. And that's why getting it right early is important. Otherwise, it's going to cost you big time in terms of cost, in terms of schedule on the right-hand side. So as a systems engineer, and I can tell you a whole bunch of aeronautical engineers know this quite well, that the left-hand side is the part that you really need to understand fully and work with all the different disciplines that are developing the system or that are part of the system design process. So again, it's aeronautical engineering, but you get into different areas too. And again, one of them is systems engineering, which, I have to say that a lot of the big wheels, as we call them, at NASA were aeronautical engineers. All right, scientific. All right, so even though you have an aeronautical degree in engineering, you can get into the scientific aspect of at NASA. And so there's something called human systems integration. This is how basically understanding how the human can be incorporated into the design of a system. And the human is treated as a system, all right? The only difference is the human is a little bit not as predictable as, let's say, hardware and software. So I have gone to know a couple of aeronautical engineers that over the years, they basically transitioned over to working in the human systems integration area, where they, get involved with doing studies of systems and how the human interacts with that system. Things like, for example, dealing with designing for minimizing human error. Okay, so you got a control system or a display system. How many errors is the astronaut or the trainee making, and why? What's happening? Is it because the switches are hard to grab? Is it because the switches are too far away to reach? The display, okay, is there too much information on that display? And people get overwhelmed with information, and so if you put a bunch of data in front of a display, it can make it very hard to figure out what's going on with the system. So it's part of I have to say systems thinking and systems engineering. And so aeronautical engineers, especially the ones that got into systems engineering, can easily integrate into working in human systems integration. Hypervelocity research. Okay, this is this is basically somewhat of an aeronautical engineering with high-speed particles that can punch holes through things. I think that's a picture. If I'm trying to remember, it was a picture of a small piece of metal that was like something like 1.5 millimeters, but it was fired at a speed of something like 20,000 miles per hour. And it punched the hole right through this thick piece of aluminum. I think the aluminum was like 2 inches thick. So it's aeronautical engineering, but at very, very high speeds, okay? And then there's the astrophysics. And of course, astrophysics, there's a major in that. But I've known one aeronautical engineer that got involved in astrophysics at this is at Glenn Research Center up in Cleveland, Ohio, in the United States. And so his involvement was working with the astrophysicists about developing telescopes. Okay, telescopes, especially for the looking far into deep space. You got to have a certain size telescope, to look, so far deep into space. But that telescope is being exposed to a a deep space environment that you have to design for. So aeronautical engineers get involved with understanding what the astrophysicist is looking for, but also assessing it from another discipline, which is the engineering aspect of this telescope. James Webb Telescope, Hubble Space Telescope, great examples. Of course, Hubble is orbiting at a very high altitude around the Earth, but the James Webb Telescope is actually way out there close to the moon. So again, understanding the environment, excuse me, understanding the environment is what aeronautical engineers are trained for. And they learn that over the years, not just from their basic training, but also from years of experience working in different disciplines. All right, so some of the duties of an engineer, this is just an example. It depends on what you're doing. Design, manufacture, and test products, okay? I can tell you early on, I did a lot of that at NASA. That was great experience for me because I became to know and understand the NASA design and engineering process. And there's a lot of documentation on that, and I had to learn many different documents, but it was a great learning experience for me. Testing, I had an opportunity to go to test facilities and test hardware to understand what are the limitations of testing, what to look out for. Testing can sometimes produce incorrect results, and you think it's your design when in fact it's the test equipment. So you got to look for that too as well. And then, the designing manufacturing is from prototype to the actual product. If you can go from the prototype to the actual product, if you can go through that whole cycle, you have learned a lot. You look at what you did in your prototype that caused problems later in your actual product. And so you can always go back and reflect on what you did and why you did it. It's important to what you did and why you did it as a documentation of learning. Okay, learning from lessons, if you will. So that's a critical part. Design, part selection, modeling, development. The design encompasses many different areas, and I have to say that when I first started my first project as a designer, I had to talk to people in areas I didn't know anything about: vibration, materials. Okay, I didn't realize materials outgas in deep space and can be toxic, and they can create a film on optics. So understanding part selection and then modeling development, understanding the model, understanding the limitations of that model becomes very important too as well. And then assess the feasibility of the design. And this comes through experience, okay? I've seen some designs that I tell the interns, I said, this is not going to work. And it's, I tell them why. Sometimes they depend very much on models, and models, they were designed by humans, and humans make mistakes. So you also have to have a good understanding of the feasibility of a design, and this becomes critical, especially when you're developing critical systems, like for example human spaceflight. I can tell you that during the design reviews, major design reviews, the preliminary design review, and the critical design review, we get deep into how feasible is this design. Sometimes the designer wants to use the best technology out there. Oh, this is gee whiz, out of the box type stuff, but they never think about, is it going to work for the application that we're using it for? And so it becomes very important to understand feasibility of a design. Evaluate design for meeting requirements. Okay, this is also important for an engineer. As he or she is designing the system, they have to look at is this meeting the requirement? And again, these are things that aeronautical engineers grow in terms of capabilities as they progress in their career. Develop acceptance criteria for a product. So what does that mean? That means that what am I going to claim as evidence that this system is going to do what you want it to. And so the acceptance criteria basically is testing analysis that shows that this system is going to do exactly what the requirement said. Like, for example, the temperature of the power supply shall not exceed 100 watts, or I'm sorry, 100 degrees Celsius. Well, I'm going to test that by basically having this power supply fully loaded and putting out as much as it can, and then monitoring the temperature of the box and seeing if it exceeds 100 degrees Celsius or not. If it doesn't, I note that and say it met the requirement. Okay, so that's my acceptance criteria, that it cannot exceed 100 degrees Celsius. And there's other requirements, the same thing. There's always some kind of acceptance criteria for a product. Support other engineers' product development. Like I said, the whole aspect of systems engineering is I have to say, the interaction of multidisciplines, and of course, teaming is very critical for this. Working in teams. Weekly reports. I know people hate writing. I'm not good. I was not very good in writing, but I had to do weekly reports. And what I did was I kept a journal, and the journal was a opportunity to not just practice my writing skills, but also writing what I did. And it was a lot easier to write my weekly report at the end of the week by just going back to the notes that I took on a daily basis, and then putting together a weekly report. The other thing about a journal is that you have a section in your journal, at least I did, on lessons learned. And so I put down things that I said, man, I did this and I should not have done that. I should have done this. I should have asked this person for more information, et cetera, et cetera. So it's a documentation of your learning process, a documentation of growing as an engineer. And then technical papers related to the work. I know some of you are going to be doing research in papers and all that, and it's an opportunity. That's another opportunity to grow your technical writing skills. And that was something that was a little weak in, and I had to work hard to kind of make up for the weakness I had there. And then meetings. Oh my gosh, too many meetings to talk about, but. Sometimes you have to do it. And I never thought I was going to go to meetings because I was a design engineer. And lo and behold, I was told to attend a meeting. And then even worse was I was told, okay, George, give me a 5-minute presentation on the status of your project. And it was like, oh my God, you mean I got to speak in front of people? That's something that some students don't like doing. I did not like doing it, but I knew I had to, and again, it was another area that I had to develop. I actually joined an organization called Toastmasters International, which is an organization to help you become a better speaker. And it was very beneficial for me. They're all over the world. I'm sure there's some there in India. You just have to look them up. We have, interesting enough, we have a couple of them here in Houston that are what we call bilingual Toastmasters International. So the Toastmaster presentations that you give and the interaction is in both English and Spanish, okay? Because we got a lot of Spanish-speaking people here in Houston. So this particular Toastmasters was geared to help those that are not very good at English, that speak primarily Spanish, to transition over to become a better English speaker. In fact, we had one that developed a little bit of an accent, almost British accent, to get away from the accent that he had because of speaking Spanish. So anyway, just something to think about. Soft skills, dealing with people. Okay, this is a biggie. All right, so there's a lot of them. I just mentioned teamwork, okay? Listening skills is not listening to somebody while you're on your iPhone, typing away. That distracts from listening to that person. Negotiating. I never thought I was going to do negotiating with engineers, but I had to learn about that. Communications, both oral and written. and I just mentioned a little bit about that. Motivating, okay, so sometimes you got to motivate people, and it can be hard. It depends on the person. And I can tell you that I've worked with very smart people, but very hard to work with. And I work with, some people that are very easy to work with. Conflict resolution, you're going to get into disagreements with other engineers. And, how are you going to deal with that conflict without basically creating an enemy? And that's something that, again, I learned by the seat of my pants, if you will. Additional skills, time management. Time management is very critical in engineering systems. If you're not meeting schedule, there's going to be issues. Being observant is actually a good skill. Making observations around your environment using your five senses, right? Your five senses of, sight, smell, taste, touch, and all that, to know your environment. Analytical, ways of methodically developing techniques for analyzing complex problems is an additional skill. And it's not you think it's what do you call it? It's a trivial skill, and it's not. Analytical is a biggie. Adaptive, you're going to have to change. You're going to have to change perhaps how you think. You're going to have to change how you design stuff, perhaps. And so you got to be very adaptive. That's something that managers look for in an engineer, is how adaptive are you to the changing environment. Diligence, okay, diligence. Well, let's see. Diligence is basically being responsible. That's basically, what diligence is all about. Some people are not responsible. They go, somebody else will do it. But, you have to take responsibility for what you've been assigned actions to. Being a curious person, you wouldn't think is a skill. You say, oh, that's a given. Not so. There are people that are not curious. They don't ask questions. They just nod their heads, yes. So anyway, these are just additional skills that I picked up along the way. That it's just, you don't have to be an electrical engineer or systems engineer, aeronautical engineers, or any engineer in general. In fact, it can apply in areas of being an accountant or even a medical doctor. So this is something that people have brought up over and over again. I'm just going to go briefly through this, is getting the job at NASA. I can't think how many times I've been asked that. And so I'm not going to say a whole bunch here, but one of the drawbacks, especially if you're not a U.S. citizen, is not being a U.S. citizen. We have a lot of internships at universities, but again, it's usually a U.S. citizenship. You can get hired at NASA by doing internships, maybe 2 or 3 years, but you also get hired for a critical skill needed, but you have to go through usajobs.gov. usajobs.gov is the a place where all the government jobs, including NASA, Department of Defense, Department of Transportation, advertise for particular skills. Now, if you're not a U.S. citizen, you say, well, what's the other option? Well, the other option is come to the United States for your undergraduate and graduate degree. And it can be difficult to land an internship, but you're gaining years of being here in the United States. As a grad student, you really have a good opportunity to land an internship job if you get the right visa. And there's different visas out there. I'm not an expert in it, but I understand like H-1B, I think, is one of them. And with a graduate degree, you could potentially land a position working with a professor at a university, and that university and that professor have a tie with NASA. And so you get to know the NASA connections, and you show your capabilities. And when you graduate, you might have an opportunity to come work for them once you get your citizenship. The approaches that I've said here, if you're not a citizen, can take years. I got to know a few people. I'm just giving you a couple of examples. One person from Indonesia came to work at Goddard, and it took 18 years for her to land that job. She became a deputy manager. Another person from India, most recently, she came to the United States 10 years ago. I was kind of helping her along the way. And so 10 years later, she's getting close. She's working on her PhD, and also landed a job as an intern at Jet Propulsion Laboratory there in California. But there's another one from, Tunisia, I think it is. And she hired an immigration attorney to help her out. So some final remarks is there's a lot of opportunities for aerospace engineers, and it can be a rewarding field. And it's not just aerospace, but maybe you want to get into something else, and that's an opportunity. And not all skills to be a successful engineer are taught in school. I can tell you from recruiters that they look for a balance in engineers. They look for a balance in terms of technical capabilities and also soft skill capabilities. Okay, so if you can put in your resume soft skill type stuff, that makes you a little bit more diverse. Okay, and you're working with people. There's no way of getting around that. And so sometimes recruiters are looking for people that are engineers that have worked with people. As I said, people can be difficult to work with sometimes, and so you have to know how to work with people. And then you fail only when you stop trying. And I realize, sometimes it's difficult in engineering, or you're not landing the job that you want to, but you haven't failed. You fail when you stop trying. Otherwise, it's just a setback. You suffered a setback because you didn't get a job here. The field of science and technology and engineering, and things just started falling into place. And I don't want to get into all the details of it, but I just so happened to take a certain path that took me to NASA, and I'm grateful for that. And I'm hoping the same thing happens for you guys. And so with that concludes my presentation. And I think we have a few minutes for question and answer. Or at least a question. I don't know about the answer. So I'm seeing questions already there. Let's see. Question about mathematical models for human factors. How do you quantify them? Not easy. And one of the things about factors approaching a qualitative way is, like, for example, workload. Okay, there's a measurement of workload that you can see how much work this is taking. That's another one, the Cooper-Harper model of, for let's call it usability of a system. And so there are a couple of them that are used in a quantitative way of assessing it. And then the other one is just observation. You get let's say five or six different people that are going to be using the system, and look and see how they approach controlling that system or using that system. And then you have to write down what your observations are, and then maybe make some form a hypothesis in terms of why you think these engineers did what they did, or these astronauts did what they did. I can tell you that for human spaceflight astronauts do a whole lot of evaluation of systems throughout the life cycle of the project. I see a question about PhD students and space science, and it depends, I guess, on what your PhD is, and but there's quite a bit in space science, related to astrophysics is one of the big ones. Another one that I think is up and coming, or pretty much has been around for a while, is called the astrobiology. Understand the biological potential possibilities of life on another planet. So, but then again, space science, you can actually somehow transition over to working with designers of telescopes. Okay, you look at you're leveraging your space science understanding to develop telescopes and sensors to measure and make observations on specific phenomena of the celestial bodies. Is there a university criteria for landing a job at NASA? Universities do not have a criteria for landing a job at NASA. Universities provide opportunities for students to get internships. If NASA has an internship available, hopefully the university notifies the student that there's an opening at NASA, and so that gives them the opportunity to go and apply. And of course, internships at NASA also happen through the usajobs.gov program. This is a lot of questions coming up here. Sir, if I'm doing my undergrad in the U.S., how could it be for me to land a job in private aerospace? Private aerospace companies sometimes are a little bit more forgiving, let's say, than NASA. So you might have a better chance working for a private aerospace company than trying to land a job at NASA. And not to say that prohibits you from working at NASA one day. I know several engineers that went to work for private companies that eventually moved over to NASA just simply because their skill was a critical skill that NASA was looking for. So there's always an opportunity there. So there's an opportunity for computer science students? Absolutely. Absolutely. What are different sectors, divisions pursuing space and astronomy in general? We are completely clueless in vast space sector. Well, I mean, the division, if you're talking about NASA, I mean, again, the astronomy and space is all related to the space part of NASA, the aeronautics to some extent, but it's the space sector. Okay, so the space sector is from designing unmanned, let's call them satellites, to robots, to human spaceflight systems. So it's quite vast. Astronomy, you can get into the general astronomy or astrophysics. I know more astrophysicists than I do astronomers in NASA, so that kind of tells you something. What does NASA specifically look for in a person, such as two people that have a time? What will they look for in the person to make a decision? I mean, if you got two people that have the same green point average and technical capabilities, they're going to go start looking at your soft skills. Okay, and the questions that they ask are usually soft skill questions. So, unless it's a very technical program, then for the most part, they're looking for a balanced engineer, one that has both the technical, but also the soft skills of working with people. Sir, as an NASA employee, you may know how many Indians are working there at NASA. I'm just asking out of curiosity. Oh boy, I want to say I got to know. Let's see, 1, 2, 3. I got to know 4. One of them retired. Actually, he was a great guy. He got a PhD in. Let's see, he got a PhD in biomedical instrumentation, if I recall correctly. He went on to become a technical manager here at the Johnson Space Center, and he's recently retired, and he goes to India quite often. So, and he's done a lot of outreach. His name is Dr. Kumar Krishnan. So anyway, if you see that name, he's a former NASA employee. What kind of computer science majors in NASA looking for? Computer science in general is something that it's a skill, right? And you can, if you learn one programming language, you can learn another. So, I can tell you that the main languages right now are, C++, C, Python, and of course, working in artificial intelligence and machine learning, developing the different learning techniques. Let's see. Technical skills needed to land a job in aerospace as an aerospace engineer. doesn't have a question on that. May I know your profile? I'm also looking forward to applying to MS abroad. Um, well, I mean, I got a profile in Lincoln, so welcome to look at that. I can't guarantee you that you're gonna, try to get. I am not an expert in finding jobs. Okay, that is not my expertise. I'm just an engineer. I was an engineer, systems engineer. I just got to learn a few things here and there, but I'm nowhere qualified to guide students as somebody else would. And that's why, some people hire immigration attorneys. Some people look for what they call student services organizations to help them. You might have an organization there in India that deals with students that want to go study abroad, and they have a bunch of students that have done it, and they got all that information and take advantage of that. So just something to think about. Okay. Um, I'm I'm running out of I'm running out of time here. Uh, I saw a question about how can I join NASA from India. I just gave a talk about that right now. Um, some of these questions I think are repeating.
Yes, sir. So for that, I think the common questions we can take in the Hexstar group itself, and talking about the other prospects where you have already covered some of the areas and sections, we would request you to share the PDF with with us so that we can share with the students and they can get some clarity. Some of might have missed that part of the portion of the session, so maybe we can do that. And yeah, we will be happily answering all the common questions to all of you, dear audience. So I think we should end our today's session, as sir also has some time limit and it's already time for the session's end, and he has questioned all of your doubts. So I think we can end the session. Sir, thank you so much. Your words were truly inspiring and have touched our audience with the purest form of information. I can see that so many of them have doubt and they were listening to you all the time, and they were highly proactive. I'm glad that the audience gathered today got the experience of such a fruitful session, sir. Thank you so much. It was really an honor to have you, and I would love to have you again on the platform of Hex-Star Universe. May you have a good day, sir. Thank you so much for joining.
Thank you. Y'all have a good day. Bye bye.
Thank you, sir. Sir, just one last request. Can we please take a selfie?
Thank you. Bye bye.
I request the audience to please switch on your videos. Just a last selfie. Are you all ready? What about others? Okay.
Are you doing selfie?
Yes, Sumit.
I'm doing the selfie, or I need to reopen my camera again.
Okay. Okay, no problem.
Actually, I had a